The cuts in the Aswan granite quarry do not match what history says made them. That is the core of what I want to explain. And the more I looked into this, the harder it became to dismiss. Let me start with the stone itself, because the stone is everything here. Granite sits at about a 7 on the Mohs hardness scale. That is the scale geologists use to measure how resistant a material is to being scratched or cut. 7 is high, very high. Even today, with modern industrial equipment, cutting granite is considered a serious job. People who work with it professionally will tell you it feels harder than ordinary steel in many situations. So when you hear that ancient people cut enormous amounts of it cleanly and precisely, that should already raise a question. How exactly did that happen? The standard answer that most textbooks still give is this. The ancient Egyptians used round balls of a rock called dolerite, sometimes called diorite. These balls are extremely hard. Workers would swing them repeatedly against the granite surface, hour after hour, day after day. The repeated pounding would slowly wear the granite down and eventually free a block. This theory is confirmed as the mainstream academic position. It is taught in schools. It is displayed in museums. Most documentaries repeat it without question. The scale that goes along with this explanation is genuinely staggering. Estimates I read suggest roughly 20,000 workers were involved in building projects like the Great Pyramid, with around 15,000 rotating through overlapping shifts, so the work never fully stopped. Some historians describe shifts of close to 12 hours. That is merciless physical labor by any standard. And on paper, if you put that many people on that kind of task for long enough, you can argue that even the hardest problems eventually get solved. Fair enough. The trouble is that when researchers actually tested the theory, it fell apart. What I find so interesting here is that a small number of scientists did not just debate the dolerite ball theory. They built replica tools. They brought in strong, skilled workers, and they struck large granite blocks thousands of times exactly the way the textbooks describe. Everyone expected the granite surface to gradually take on the appearance of the ancient marks at Aswan. It did not. The marks the hammers left were rough and uneven. Some hits cut deep, others barely scratched. Every blow landed slightly differently. Edges crumbled in places. In other spots, the surface splintered. There was no clean spacing, no graceful curve, just the honest, messy result of repeated human effort. And what made this experiment so revealing was not simply that it failed. It was the specific way it failed. The harder the workers pushed, the messier the surface became. Speed made errors worse, not better. Fatigue set in within the first hour, and grips loosened, angles shifted, spacing wandered. Because that is what a living body does. It is not a flaw, it is biology. Now compare that to what the actual marks at Aswan look like. Long, sweeping, curved cuts running across the rock in near identical spacing. They flow into each other the way ripples move across still water. No jagged breaks, no scattered chaos. Almost everyone who sees them for the first time reacts the same way. They lean close, go quiet, and ask the same question out loud. Are these really thousands of years old? Because at first sight, they look exactly like the output of a modern machine. That gut reaction is what pointed researchers toward a more careful analysis. Instead of relying on human opinion, they fed the Aswan data into an AI system. But first, they built the dataset properly. They used a technique called photogrammetry, which involves taking thousands of overlapping high-resolution photographs and stitching them together into precise three-dimensional digital models. You can rotate these models, zoom into them, and measure from any angle down to very fine detail. All of that went into the AI. Here is the part I think matters most. The AI was not told this was Egypt. It was not told what tools might have been used or what conclusion anyone wanted. Its only job was to measure patterns and compare them against thousands of known tool signatures in its database, both ancient and modern. It worked through 847 separate cuts. For each one, it measured the curve, the arc radius, the entry angle, the depth, the spacing between neighboring cuts, and the consistency across the entire surface. Then, it compared all of that against everything in its database. The result that came back was a 4.3% total variation across all 847 cuts. To me, that number is the centerpiece of this whole thing. Let me explain what it actually means. When a skilled person using good modern hand tools repeats one motion over and over, natural variation between 12 and 20% is considered completely normal. Even reaching 22% surprises no one, because a person is not a machine. The angle of every swing drifts slightly. Force changes. Grip loosens. That drift is just part of being human. And yet here were hundreds of cuts spread across a working quarry with a total variation of only 4.3%. The AI also flagged that entry angles were strikingly consistent across all the cuts, as if every stroke had been planned in advance and then executed with mechanical discipline. When the AI ran the marks against its full database to find the closest match, 3 modern tools came back at the top: diamond rotary cutters, high-pressure water jet systems, and ultrasonic cutting tools. What separates all 3 from a hammer is not just sharpness, it is repeatability. A machine does not tire on the 400th pass. It does not shift its grip or drift in angle. It makes the 800th cut the same as the first. That sameness is what the AI kept finding in the Aswan marks. The closest match was classified as industrial rotary cutting. Confidence level, roughly 94%. Researchers looked under a microscope and things got more specific. When you hammer hard stone repeatedly, the surface fractures. Tiny crystals inside crack in random directions. Under magnification, hammered granite looks rough, full of splinters and stress lines spreading down into the material. The Aswan surfaces looked nothing like that. What researchers found instead was something called a shear pattern, a clean, sharp boundary between the cut and the untouched stone beside it. It looked like material had been deliberately separated along a chosen line, not broken apart. And below the cuts, there was almost no damage extending down into the stone. If hammers had done this, cracks should spread downward. They were not there. Under higher magnification, very faint spiral marks appeared. tiny rotating patterns, suggesting a spinning tool had traveled across the granite while turning continuously in one direction. Samples from completely different parts of the quarry showed the same spirals running the same way. Researchers also found signs of concentrated heat at small specific points. Not the spread of heat from two stones grinding together, but heat pinned to a tight rotary contact zone. That is the heat signature of friction under a fast spinning blade. And then they found microscopic particles of corundum, which sits at a 9 on the Mohs scale and is used today as an abrasive in industrial cutting discs. In some spots, carbon structures that several researchers described as having a diamond-like form. Any one of those details alone you could debate, but stacked together, they describe a tool. When the AI processed the full picture, the spirals, the clean shear, the minimal internal damage, the pinpoint heat, the hard abrasive particles, it returned the same conclusion. This was not the signature of dolerite hammers or any Bronze Age tool. The closest match was industrial-grade diamond abrasive rotary cutting. The shaft problem makes this even harder to explain away with the old theory. Scattered across the Aswan site are deep, narrow shafts. Some drop roughly 30 to 50 feet straight down and are only 3 to 4 feet wide at the mouth. Inside those shafts are the same curved uniform marks found across the open quarry above. Same depth, same pattern, same precision. But here is the physical problem. To swing a dolerite hammer hard enough to actually break granite, a worker needs real room to move. At minimum 18 to 24 inches of clearance to draw the hammer back before striking. That backward arc is where the force comes from. Take away that arc, and you take away all the speed. A dolerite ball pressed gently against granite does almost nothing. The hammer theory depends on momentum. Remove the swing, and you remove the method entirely. In those narrow shafts, that swing is physically impossible. And yet the marks on those shaft walls are identical to the marks in the open areas above. No loss of precision, no loss of quality. The AI analyzed the shaft geometry and the cut patterns together and placed the situation in the category of physically impossible due to spatial constraints for a tool requiring a backward swing. A system applying straight downward pressure from the front with no backward motion could still function in that space, which quietly removes the one method the textbooks insist was used. Now I want to add something that does not get talked about enough. The unfinished obelisk, still lying in the quarry, still attached to the bedrock where it was first carved, is what would have been the largest obelisk ever attempted. Finished, it would have weighed over 1,000 tons. The mainstream explanation for why it was abandoned, work appears to have carried on after the fracture had already formed. If the crack were truly the reason the project was abandoned, the marks should stop right there. They do not. And the marks on this giant unfinished stone are identical to those found across the rest of the site. Same curved arcs, same even spacing, same level of precision. Even in the lower sections where the working space narrows considerably, the quality of the cuts does not drop at all. So what actually stopped a 1,000-ton project so suddenly that no one ever came back to finish it? That question still has no clean answer. The timeline reversal is where this becomes genuinely hard to process. Red ochre paintings sit directly on top of some of the cutting marks. That ordering matters. The stone was cut first, and the paintings came later. When researchers dated those paintings, some estimates suggested they could be nearly 2,000 years older than the early dynastic civilization of Egypt. If the paintings are that old, the cuts beneath them are older still. That places them in what is called the pre-dynastic period, a time when mainstream history says only scattered small groups lived in the region, equipped with the simplest stone tools. Then the AI ran what it called a temporal precision analysis. It compared the geometry of cuts against their estimated ages. The result came back at roughly 91% confidence and ran completely backward. The older a cut appeared, the more precise and uniform it was, moving forward through time toward more recent periods. The cuts grew rougher and less controlled. The pattern was tested statistically, and according to the report, it reached the 99th percentile of statistical significance, extremely unlikely to be chance. Every civilization we know of improves its technology over time. Early work is crude, later work is refined. The Aswan data tells the opposite. The oldest work is the finest, and precision appears to fade as centuries pass. To me, that is the most unsettling part of all of this. It suggests something was known at the very beginning that the people who came later simply did not have access to anymore. And that idea, that knowledge can go backward, that a civilization can lose something so completely it leaves almost no trace, is not comfortable to sit with. There is one more layer I want to add here, because it changes how I think about the people who made these cuts. Granite is not uniform on the inside. It contains different mineral bands, harder regions, and natural weak veins, where the rock splits more easily. Engineers today call these grain boundaries and internal weak zones. Modern quarry crews use sonar scanning and ground surveys to find these features before they cut, then plan their paths to follow the lines of least resistance. Many of the old cuts at Aswan appear to follow those same natural weak zones, as if whoever made them already understood which parts of the stone would yield most easily, without any scanning equipment at all. The outside surface of a granite block tells you almost nothing about what is happening a foot deep inside it. To follow internal weak lines consistently, by hand, without instruments, would require either extraordinary luck repeated hundreds of times in sequence, or some method of reading the inside of a rock that we currently have no record of. When the AI compared surface mineral mapping against the cutting paths, it found a real relationship, concluding at roughly 88% confidence that the cut paths appear chosen according to the internal structure of the stone. Some researchers have started calling this the stone reading theory. The idea that whoever built here could understand the hidden architecture of granite before ever touching it. The same cutting signatures do not stop at Aswan either. When researchers ran the Aswan data against granite at the Valley Temple of Khafra at Giza, one of the oldest granite structures in Egypt, the same microscopic patterns appeared. Clean cuts, minimal internal fracturing, faint rotating marks. And when the AI measured the difference between cuts at Giza and cuts at Aswan directly, variation came back under 5%. Two different locations, different blocks, different periods, and nearly identical cutting method. To me, a single skilled workshop or one exceptional generation of workers could explain one location. You could just about argue that. But the same signature appearing hundreds of kilometers apart across multiple sites with under 5% variation is not a workshop. That is a standard. That is the kind of consistency you only get when an entire civilization is using one method and one class of tools. And somehow that shared standard disappeared from the record so completely that we spent centuries insisting it never existed. What I keep coming back to is this. The current dolerite hammer theory is confirmed as the accepted academic position. It has decades of institutional weight behind it. I am not dismissing that lightly. But the physical evidence, the AI analysis, the microscopic data, the shaft geometry, the reversed timeline, and the internal stone mapping all point toward the same uncomfortable gap. The marks do not match the tools. The tools do not fit the spaces. The oldest work is inexplicably the most precise, and the same method appears across an entire region as if it were standard practice, not an accident. Something cut that granite, something consistent, controlled, and precise. And whatever it was, we have not found it yet. Or maybe more accurately, we have not yet admitted that we need to look. So for me, the main thing I take away from all of this is straightforward. The stone is not agreeing with the textbook. And until someone produces a physical recreation that actually matches what is carved into that quarry, with the same variation score, the same microscopic shear pattern, the same spiral marks, the same pinpoint heat zones, the gap between what history says and what the rock shows is not closing. It is widening, one cut at a time.